So let me start by recapping what I talked about last time, and then I'll say what's coming up in this talk. So the main point of the last 2 weeks ago was that there's this correspondence between the classical Teichmüller space and the Segal moduli space, and then just because maybe the general definition of the Teichmüller space is unfamiliar to a lot of people, I'll just remind you about it. So you look at the set of quasi-conformal deformations of a fixed surface. So F here is a quasi-conformal map, and sigma 1 are Riemann surfaces. And then you say that two of these triples are equivalent if there's a biholomorphism, I should say. If there's a biholomorphism between the two image surfaces, such that if you go around the triangle F2 inverse of sigma of F1, that's homotopic to the identity. And the key thing here is you have to say rel boundary. And rel boundary means the homotopy keeps the boundary fixed throughout the homotopy. So it's actually, in particular, it is identity on the boundary. So a couple of things I want to mention. So I just want to make a couple of things clear. If you have, generically speaking, you'll have an extension of the quasi-conformal map to the ideal boundary. So if you have the quasi-conformal map on the interior of the surface, it will extend uniquely to the boundary. On the other hand, if you have some function on the boundary, it might have many quasi-conformal extensions to the interior. Okay, so that's the definition of Teichmüller space. And the thing is, this condition rel boundary, which goes back to Burrs in the 60s, this means that it's a big space. So if your F, the different ways it deforms the boundary are sort of included in this Teichmüller space. Now, in the Segal moduli space picture, the same thing appears independently. So here, this is the Segal moduli space. It's quasi-symmetrically rigged. So normally, the convention is to use smooth or analytic boundary parametrizations. But if you extend that to what's called quasi-symmetries, which are the boundary values of quasi-conformal maps, then you look at the equivalence classes. Here, sigma is a genus G and surface with n borders, homeomorphic to S1. Technical point I didn't say last time, just in case anyone cares. When you say it's a border, that's a strong condition. It's a particular kind of boundary, which is sort of conformally invariant and God-given in a way. So the border here, it's not just boundary, but this is a technical point in case anyone is into this. So you have such a surface, genus G with n boundary curves, and you have n boundary parametrizations by the circle. And typically, as I said, those are usually taken to be smooth or analytic, but we'll choose them to be quasi-symmetric. And then you look at Riemann surfaces together with this data, the boundary parametrization, modulo conformal equivalence. So you say that two elements are equivalent if the Riemann surfaces are conformal to each other, and that conformal map carries one boundary parametrization to the other boundary parametrization. And so conformal maps also have a unique extension to these border curves by some general theorems. There's also a puncture model. So instead you have a Riemann surface genus G with n punctures. So instead of looking at the boundary parametrizations, you can use the boundary parametrizations to sew on disks. And then the sewing map extends conformally to a disk. It's a little bit counterintuitive, yet you have this irregular mapping. But after you uniformize, you really have a conformal map from the disk into the surface. And you have to just assume that you have, I didn't write all the conditions here, but you have a number of maps into the surface. Each one takes 0 to a specified puncture. preserving the order, and they have to have a quasi-conformal extension to a neighborhood of the disk, of the closure of the disk. So the equivalence of these two models is sort of folklore in the Segal picture. But we also proved it in this situation, which just involved a couple of technicalities. It was no big deal, really. But then, now once you have that, if you decide to extend from smooth to quasi-symmetries, then you get this connection between the Teichmüller space and the Segal moduli space. So what's the connection? Here it is. Like, so, okay. My wife always tells me, say the answer first. So I'll follow that rule. So the Segal moduli space is the Teichmüller space quotiented by a nice modular group. So this is a nice, discontinuous group action. What is that group? You have what's called the modular group. So you look at quasi-conformal self-deformations of the surface, and I put the P there to say it's pure, so that it preserves the ordering of the boundaries. And then you look at those which are homotopic to the identity route boundary. So in particular, they are the identity on the boundary. And then the modular group is just the quotient of all quasi-conformal deformations by those which are homotopic to the identity. And these act on Teichmüller space by, I guess I should have written that action down. Can I use this cloth to wipe the board? Do people do that, or is that? Am I going to violate? Okay.
Wash it afterwards.
Okay, I'll wash it after. So the action. So the action on an equivalence class. You just compose your mapping by row inverse. And you have to put inverse there to make an actual action, otherwise it anti-acts. So then if you restrict to those which are the identity on the boundary, this is, I call it P mod I for identity on the boundary, P for pure, then that is the quotient, that's the group that you have to act on the Teichmüller space by to get the Segal moduli space. So that's the recap of the picture. Let me emphasize 2 points. One is that there's an analytic thing going on, which is that you make a change in the analytic condition, but then that allows you to see a geometric fact. The geometric fact is that these two spaces are the same, somehow morally. And I think it's comparable to, for example, if you're dealing with Fourier analysis, I mean, you can talk about, say, smooth functions and Fourier series of smooth functions, but then if you want a nice Hilbert space, you want nice algebraic relations for everything, everything becomes very clear once you say we're going to use L2. Now you have a Hilbert space, you have your decomposition on orthogonal basis, everything makes complete sense algebraically. So this is, in my opinion, analogous. You make the right analytic completion, and now you see a geometric connection very clearly. Okay, so that's a summary. Maybe I should stop at the recap before I move on. Were there any questions? Yeah, I don't know if that's good or bad. Okay, so now what do I want to do today? I want to divide it into 2 parts. The first part, I want to talk about consequences of this correspondence. And then afterwards, I want to talk about the Weil-Petersson. I want to use it at the second hour for Weil-Petersson, hopefully a little more. I'm going to try to start before the break. So the Weil-Petersson moduli space is when you change the riggings to Weil-Petersson quasi-symmetries, in a nutshell. And then I want to talk about that. Okay, so let me start with consequences. So by consequences, I mean consequences of this correspondence. So the first consequences are in the direction Teichmüller theory to conformal field theory. So we have the following theorem, maybe the first thing. We have that the Segal moduli space are Banach manifolds. So why is this true? Because classically, this goes back to the 60s, the Teichmüller space is a Banach manifold. That was established by Schippers, a large number of people. So then, because this modular group, we just needed to show that it acted properly discontinuously and fixed point freely. It actually acts by biholomorphisms. That's essentially a classical fact. The fixed point freely was we had to just beef up some known theorems, and we were able to show that. But once you have that, this is acting by a discontinuous group of biholomorphisms, and therefore these quotients are also Banach manifolds. So we have a complex structure. So and one of the things that okay, maybe let me write one more thing here. The sewing operation is holomorphic. So in the Segal moduli space picture, you have, if you were here for Andre's talk on the workshop a couple weeks ago, he talked about this picture. You have this sewing operation on the Riemann surfaces, and the Riemann surfaces together with the boundaries, they are morphisms in a certain category of Hilbert spaces. So you have the Riemann surfaces map between circles, and then you have a projective holomorphic functor, I think, from the space of circles with the Riemann surfaces between them, and operators between Hilbert spaces attached to those circles, or of tensor products of those Hilbert spaces. So, and there's supposed to be a holomorphic structure on that. So you need a holomorphic structure on the moduli space, and you want sewing to be holomorphic. So this is solved by this problem, if you accept that this is a good model, analytic model of the moduli space. And then the third thing I want to mention, and this is kind of automatic, and we use this in a number of publications later, that the tangent space, I mean, you have the Teichmüller space also classically has a well-defined tangent space, and it's completely understood how this works, which means because this is quotiented by a discontinuous group, then you have a tangent space on the moduli space too. So actually, you know exactly what the infinitesimal deformations are. This comes automatically out of this picture. And so we use that in different ways in different publications, but I'll just mention it here. It's sort of you get that for free from the first 2 points here is what I want to say. The tangent space, and I'll say at the identity, this is modeled by omega minus 1 sigma, and this is a little bit technical. You take the hyperbolic metric, and you multiply it by complex conjugates of quadratic differentials on this surface. So, I don't know, probably you don't remember this notation. This is an L infinity space of quadratic differentials on sigma. And if you take its complex conjugate and divide by a power of the metric, this thing will now transform like a Beltrami differential. And this is exactly the tangent space at the identity. Now, there's a whole big story behind that. If I wanted to go through this very fully, I'd have to talk about a bunch of things. You know, it's usually a chapter in a book on Teichmüller theory describing the tangent space. And then at the identity, this is literally true. And at other points, you have to move it around with a change of base point. But the bottom line is you get a very nice description of the tangent space of all the modular spaces.
So lambda is the square root of the
Yeah, I guess, yeah. Let me just count make sure I'm not making a mistake.
Yeah,
So
divide by the hyperbolic metric, so either lambda is the square root or lambda is the latest type of...
yeah, let me just count for a sec. So I get dz squared. Yeah, so I want that lambda is the square root of the hyperbolic metric. So lambda to the -2 is 1 over the hyperbolic metric.
So why is the square root of the hyperbolic metric more relevant than the actual hyperbolic metric?
I don't know. I mean, it's just a convention. Some people use this convention, other people don't. Okay, any other questions? Okay. Yeah, maybe I should make this non-ambiguous though. So, let's see. Yeah, the whole thing is 1 over the hyperbolic metric. So. Okay. Let's see, so then the other direction, so now CFT to Teichmüller theory. Red. Is that this tells you that the Teichmüller space has a fiber structure. And I mean, this is an unknown fiber structure, so you won't, there are other fiber structures that people refer to in literature, but this is a new one. Is it hot in here, or is it just because I'm saying? No, a little bit, okay. Okay, it's too nice outside to have air conditioning on though. It's sort of crazy on a daily. Yeah, I wouldn't mind. That would be nice. Hopefully it won't get too loud. So let me draw a picture for this. So this is actually, there was no theorem in CFT that actually gave a theorem in Teichmüller theory, but the picture did. Once you have this picture, that you have the Riemann surface together with the boundary parametrizations, then you right away think that now you have this sort of fiber structure that somehow you can model the Teichmüller space as some small space together with the boundary parametrizations. And so you can do this. Let me draw a picture. So if you look at the Teichmüller space of the bordered surface, and if you decide to sew on some caps, and I use this, you choose a base rigging tau. space parametrization. Then, if you sew on the caps using your tau, you get a compact surface, R sub tau, and what you have here is you take the Teichmüller space of this punctured surface obtained by sewing on caps, and this is a finite dimensional space. And then what's the information you lose when you go down from this one to this one? If you look at the deformations of this compact surface, you're losing the information of the quasi-conformal deformations on the boundary, or roughly equivalently, the parametrizations in the Segal picture. So you have this vibration that T of sigma is, roughly speaking, the finite dimensional Teichmüller space fibered over by the riggings. And I think it's a natural idea to try to construct a Teichmüller space by taking the, or a moduli space by taking the Teichmüller space and adding in riggings. But the content here is that that space already existed classically. Okay. So what I'm going to do is, first I want to talk about this fiber structure. And I could go on about that for a long time. But I want to get to Weil-Petersson, so I'm going to try to do that give a very short introduction to this fiber structure, and then try to start Weil-Petersson before we go to the break. Is there any questions about this? Yeah?
Question about this. So this doesn't seem like if you do a reparametrization of one of the boundaries, so you compose by some quasi-symmetric map on S1,
yeah,
then you'd get a different thing in the bottom, right? Because you
that's right. Yeah.
You glue on a disk, but it's different.
So that's
what are the? Is there some other action that this fiber structure is invariant under?
Oh, I see what you mean. Yeah.
So I would somehow want to see the fiber structure forgets the parametrization. But
Yeah.
it turns out that if I change the parametrization by composing with some reparametrization,
Yeah.
which I would find somehow natural, then
Yeah.
it turns out I don't forget all of that information because I
Yeah.
remember some.
So it turns out the fibers are clear in the puncture picture. You fix the surface, and then you think of all the non-overlapping mappings into the punctured surface. And now, if you forget those over a fixed punctured surface, then you always get that fixed puncture surface. So that's exactly the fiber over. I'm also lying, there's another modular group action in there, but essentially, this is what you're looking for. In the boundary picture, it doesn't work so well because with the boundary parametrizations, it moves you around on the bottom space. Yeah, that's exactly right. I'm going to be specific in a minute. Any other questions? Okay. Yeah, so I think I'm going to give the shortest version of this. There's a bunch of details that would be fun to get into, but I think I'm going to avoid it. So now, let me define the map specifically. So we define this map C tau, which takes T of sigma into T of R tau. And the picture is you have, let's say you have some fixed Riemann surface sigma. And you have your quasi-conformal deformation into a new one. I should pick a Riemann surface with less boundary curves so it's quicker. So now you have your base parametrizations. And you can think of this base parametrization as being also like choosing the base surface in the Teichmüller space. So you decide what point you're going to deform from. So there's also a decision here what riggings we're going to deform from. So now you sew this on. You get a new surface, R tau. And now you get a new quasi-conformal map, which I'm going to call F tau, into an R1 surface. And we're actually going to forget about these curves. And what we do is we take, so C tau of sigma F sigma 1 maps to R tau F tau R1, where here mu of F tau is given by this extended Burr's trick. So it should have the same Beltrami differential as F on the original surface sigma, and then on these caps, you set it to be 0. And let me just say what I mean by the caps. I mean these things. Omega is the union of these things, the caps that you get. So that means, actually, it turns out that this F tau is conformal on the caps, but in the Teichmüller theory picture, we just forget about those. So this is still in the picture that was a little aggravating in terms of understanding the fiber, but you can let me try to. No, I'll try to give a better answer to your question, a precise one. Any questions about this map, though, before I... No? Okay, so let me give a more precise description of the fibers. So now, for a fix, so let R be punctured. Genus G and punctures. So we say OQC of R. I think I defined this last time, but let me just repeat it. It's a set of mappings F1 to Fn. such that, and I know this is not much of a definition, it's just that the conditions on these is a little long, so let me put it here. So 1, so each fk takes the disk conformally into the surface and also takes 0 to the kth puncture. And secondly, we want this to be quasi-conformal extendable. That's in order to meet the condition that this relates to Teichmüller space. And then finally, the closures of these don't intersect. And then we have the following theorem. OQCR is a Banach manifold. Locally modeled on a 1 infinity of d plus c raised to the nth power, or n direct sum. I can't remember whether I defined this last time, but I'm going to do it again, obviously. So this is a space of 1 forms. So A1 infinity of sigma is the set of 1 forms such that the L infinity norm is bounded. So what you do is, this is a 1 form, so to turn it into a and to turn the absolute value or the modulus into a function, you have to divide by a power of the metric. So e.g. in the disk, we would say, let's say this is the set of HDZ such that the suprema of 1 minus, I should have said this is a holomorphic 1 form. That's important. 1 minus mod z squared mod h is less than infinity. So if you're in the disk, this looks like an arbitrary weight that you just throw in there. But if you're on a Riemann surface, you know this is not a function. This is a differential. You express it in local coordinates. It changes. The function changes. So one then sees why such a factor has to come up if you're going to define something invariant. There could be other choices, but this is, this works. But by the way, actually, for Guillaume's question here, you do need the square root of the hyperbolic metric in order to get a well-defined have this thing here, this modulus should transform like a real function. So in other words, no, it's actually invariant interchange of coordinates. Okay. Let's see.
One question, so maybe
Yeah.
can you explain again how the picture on the... So if you're interested in showing that O quasi-conformal R is a Banach manifold, and we already know that, I guess, the TF sigma is a Banach manifold, then how does the picture on the left-hand side help you to maybe deduce the fact that O of QC of R is a Banach manifold?
In fact, this is a separate theorem.
Ah, okay.
Yeah, so actually, you could, you can say, you can prove that the fibers are submanifolds of T of sigma, but this is a separate fact that you can get a complex structure directly on these things. And the fact that those complex structures map gives you a strong match, gives you a stronger theorem that this is actually an embedded submanifold of a certain kind with respect to this complex structure. So there's actually a stronger theorem here. This was not deduced from that. I was going to say that actually, but thanks for the question. It anticipates what I'm going to do. So let me draw a picture about the Banach manifold structure because it's kind of fun, and I haven't had a picture in a few minutes. So let's say you fix some Riemann surface here. What you do, I need some colors here that I haven't used. So let's say you have some mappings. Just try to draw less of them this time. So put those over here. And what we want to do is talk about, the structure as you change these mappings. And locally, if you take some open neighborhood of the closure, I won't go into too much detail, but take some open neighborhood of the closure of the images of the Fs, and take some mapping into the plane. I'll just draw one of them. I guess it's zeta 3. So take some conformal map of a neighborhood of the purple thing. And now, what you do is you map F1 to Fn. This maps to A of zeta 1 of F1, zeta 1 of F1 prime at 0, all the way to A of zeta of Fn, zeta n of Fn, zeta n of Fn prime at 0. Let me define what I mean by A here. A of G is just a pre-Schwarzian of this mapping. I apologize for using A again, because I was using it for the spaces, but Takhtajan and Tio and a couple other people use A for the pre-Schwarzian, so I thought I want to just keep using that notation. So now, essentially you have to prove a bunch of things. Like if you jiggle these mappings in, and if you jiggle the mappings inside the Banach spaces, the pre-Schwarzians jiggle. You don't want these maps to move outside of your domain on some open set, and you can prove that, and then you can say that this is a local coordinate system on OQCR, so the space of riggings. Any questions about that? Okay. And then maybe someone asked, I can't remember who asked it, but someone asked about the importance of the Schwarzian. And I mentioned that when it comes to in the Segal picture, you have to keep track of more. So if I could use the Schwarzian here instead, but I'd also have to keep track of the pre-Schwarzian at a point. So I'd have to have 2 copies of C. So one really needs more information to capture the riggings than just the Schwartzians. One needs this greater set of information. Okay, so now let me say the theorems, and this will answer Lewis's question, and Sid's, I hope. Where the heck was I? I'm going to skip that. So we have the following theorem. I was not making good use of space here. Okay, I'll just make this work. So first of all, C tau is a holomorphic fiber map. And it's a little stronger than that. So it's a holomorphic map, and it has local holomorphic sections. Equivalently, it's a submersion. So that means you really have that this thing is somehow a submanifold. But moreover, the fibers are locally biholomorphic. To this Banach manifold. So A1 infinity V plus C to the n. And actually you can be specific about what the fibers are. Now to answer Sid's questions. So the fiber over, say, R tau F R1 is locally biholomorphic to OQC of R1. So that's the answer to your question, Sid. So you get a nice description of the fiber now in the puncture model. And Lewis, this is a strengthening. It's not just that you have a submanifold, but the submanifold is biholomorphic to this specific submanifold structure you construct here, which also leads to a nice set of coordinates. So you get, I'll just mention there exist coordinates which separate T of R and A1 infinity. I'll just say and the fibers. Okay. Any questions about that? Yeah.
So in CFT, we also consider sometimes like punctures on the boundary. So is there a similar story where you replace like the disk with a half disk or something like this?
So the punctures are on the boundary. Okay. I mean, the obvious answer to your question is you could use the half disk instead of the half plane instead of the disk, but that's not what you're asking. You're asking about whether I can deal with marked points on the boundary. Yeah. No, this does not occur in this picture, but it's a really interesting thing. There's a whole bunch of completions that one wants to further take after seeing this, and then one wonders whether they're related to compactification, so Teichmüller space and things like that. So, yeah, it's an interesting question, but in this picture, no, we can't deal with that. So. Any other questions? Okay, so maybe I'll try to get started on the WP structure, and then maybe stop in about 5 minutes-ish for the break. Let's see if that works okay. Because I know actually, I think a lot of people would be particularly interested in WP. by Weil-Petersson, so I want to try to at least get there. If you want to have some fun, there's some stuff I left out of the talk. You can think about, you can try to see why I said only locally biholomorphic. So there's actually a modular group sitting in the background that I haven't mentioned yet. And if you like geometry, you can sort of try to think what the precise statement is, or sorry, not the, it's already precise, but what a improvement or an improvement of that statement is. One can actually improve it a little. So the fibers are not quite OQC. They're a little bigger than that. Okay. Okay. So now let me start with the summary of the complex structures. And here I want to say just a philosophical point, or maybe even a historical point. So the history of Riemann surfaces and moduli spaces, it's really all about, it's full of the story of what are complex structures on those moduli spaces. So, you know, going all the way back to Riemann, there are different ways of describing the moduli space itself as a manifold. So you want to say that it has some complex structure. For example, the period mapping is one way to do it. So you look at the period mappings are holomorphic parameters on the moduli space. That was already laid out by Riemann. And then one can say that Riemann was only talking heuristically, but I think you have to cut the inventor of the concept of Riemann surfaces, manifolds, and modern differential geometry some slack if you know you think that their proof is not rigorous. I think that, you know, having invented the concept in the first place is kind of an accomplishment to actually prove some of the deepest theorems right away, albeit somewhat heuristically. So it's widely believed that, I mean, the rigorous proof of the period mapping being holomorphic was Alforsch, and then other complex structures were given by Teichmüller, and then there's always in CFT there's this people want to understand how you can sort of holomorphically move about in the moduli space. So it's this idea of the complex structure of the moduli space. It just goes way back, and it just the story does not end. So now, just in the sort of classical Teichmüller space, the Alforsch-Burrs picture, let me just summarize some of the complex structures. We have one from the Burrs embedding, which I talked about last time. If you remember, we had T of sigma mapped into a space of holomorphic quadratic differentials, actually on the double. We have the tangent space structure. And I didn't talk about this one too much because it's a long story. So at the identity, it's given by these, what's called the harmonic Beltrami differentials. Oops, sorry. And so then there's a whole story in the 1960s picture that you can describe the tangent space that gives another complex structure on the manifold, essentially by exponentiating the tangent space. So locally, this is actually a model. This can be used as, if you describe the tangent space, then it also gives you a local coordinates just by exponentiation. So this is another complex structure. And then we also have this new fiber structure. Okay, and I could list many, many more, but I just want to isolate three that from the top. So you have this you have this local description, complex structure in terms of these rigging coordinates. So this is the third new fiber structure on Teichmüller space. Okay. So I think I'm just going to give a quick maybe it's best to stop now. I'll start Weil-Petersson afterwards. Maybe, okay, yeah, let's stop here.